Yeah, when we get started. I think it's just about time to start. Who's pretty good at math? Anybody in the room pretty good at math? Yeah. Anybody ever been at a restaurant where you're with a bunch of friends and everybody's going to pay for sort of their share of the meal or whatever, and had the waitress or waiter say, "Oh, would you like me to split that up on separate checks?" Anybody ever reply to the waiter or waitress, "Now we're all pretty good at math"? No? Guess that's just me. All right, so somebody's pretty good at math. Ooh. 39. No, this way. This way. Divided by 72. What's 39 divided by 72? Quick, somebody. Siri, what's 39 divided by 72?
It's about 0.5416.
Call that a 2, right? We can round that. Batting 542. That's pretty good for the middle of the season, huh? Baseball people here? Batting 542 would be pretty good for the middle of the season. I got 54. Let's call it 55. 55% of the students in class today. That's pretty cool. I don't know how many are watching live. 2. Wow, that's pretty sweet. One of them might be me. The other one, I don't know who the other one might be. Don't skip class next week. unless you have to because you're in quarantine or isolation or something like that. Next week is going to be cool. Can't say much about today, but next week is going to be cool. Don't skip class next week. All right? You guys got that? We will light stuff on fire next week. We will eat stuff next week. At least I will. Maybe you guys will. I don't know. We will light stuff on fire. We will eat stuff. And yeah, we will do math. We might do some math on the board. I guarantee you that if we're doing math on the board, I will operate the chalk. And I will be taking dictation. I will write down what you tell me, even if I think it's wrong. It's up to you guys to catch each other's mistakes. Because I have experience with this. I've been doing this for almost 20 years. And I know that if I try to do math on the board, I will make a mistake. Therefore, I'm going to let you guys make the mistakes and catch the mistakes. If I see a mistake and notice it as I write it on the board, I will try to draw it out of you. But don't count on me. Just like don't count on the automatic grading of the quizzes in Canvas. Because even if we know there's a problem with it, we cannot fix it. We must go fix each individual person's grade individually after the quiz is over. So, if you know the answer is the correct answer, answer the correct answer. Don't answer the one that the automatic grading thing tells you is the correct answer. Be confident in your math. All right, so I promised we would start today with a haiku. Feed, speed, depth of cut. Guessing, not recommended. Carbide, explosion. Actually, there's a couple of haikus sprinkled through today's lecture. Pretty excited about haikus. I could tell you the story about, you know what? There's a YouTube video that tells the story about why I'm excited about haikus. So you can go search for it. All right. What are we talking about today? We are going to talk about feeds and speeds. What are we talking about today in general? I feel like a star because the lights are shining on me. I think it's the projector. Maybe I'm seeing stars because of the lights. What are we going to talk about today in general? So we're going to talk about feeds and speeds. We're probably going to talk about CNC machining, right? Because we talk a lot about CNC machining in this class because CNC machining is the most important manufacturing process in the world, and or because we have a lot of CNC machine tools in the lab, so it's easy for us to give examples of the things that we talk about in the class by doing it in the lab, and or because I think it's cool. All those are good reasons to talk about CNC machining. But why? What's the theme of the class? What's the fundamental theme of the class here? See if I can make this projector go up. Mute right. Hey, that's the right one. And somebody say, what's the theme of the class? Well, there's a general word, right? Is it manufacturing? Right, and so manufacturing, we said, is making stuff with the intent to sell it. I'm going to sell stuff that we made. To whom? This one's easy. Who do we sell the stuff to? Customers? This is exactly why I say don't skip class next week. Because it's exactly why I like to try to make week 3 of the term. Next week's week 3, right? It's approaching hump week. Yesterday was hump day. We're approaching hump week in the term. I find that if I don't make week 3 really exciting, my batting average falls way off at the end of the term. So this is why I'm even, what do we call this? This is like the lead. This is the lead into it, right? The leadoff batter, right? I'm setting you up. I gotta load the bases before I can hit that grand slam next week. Too much baseball on the mind. I don't know why. I don't even really watch baseball. But all right, so be here next week. It'll be fun. Manufacturing to sell stuff to our customers. Okay. So that's the main theme of the course. Today we're talking about feed speed and depth of cut. Feed and speed and depth of cut are things that we call process variables. Why do you think we call them process variables? Come on, quick, somebody. They're variable because we get to change them. We, as the manufacturing engineers or the manufacturing operators or the CNC machinists or the machinists, we get to pick them. So because they're variables. They're process variables because they control the manufacturing processes that make the stuff that we want to sell to our customers. Does that make sense? That's why we call it process variables. Let's take a step back in the process of manufacturing, though, in being a manufacturing company and having stuff we want to sell to our customers. Let's take a step back. What's the first thing we have to do? We have to know what our customers want, right? So the customers have needs. Customers have needs. We'll call them customer needs, conveniently. Then we have to take these customer needs, because customer needs can be pretty amorphous, right? I want a quality automobile, right? And we already talked about the fact that quality is pretty amorphous. Amorphous? Not morphous. Has no morph. Customer needs. Engineers take customer needs, interpret. Who's seen the movie Office Space? Really? Be proud if you've seen the movie Office Space. I want to see hands in the air. One hand in the air. What's your name? Because I'm just going to give you an A now. Caitlin. Caitlin gets an A in this class. She does not need to come to any of the lectures. Shit, it's on camera. I don't think I'm allowed to say that. I could think it, though. All right. So what's the best scene from the movie Office Space?
I think it's
The final one? All right, that's pretty cool. It does sort of, it sums up the what's the story that teaches a lesson? It's a proverb, but there's another word for that, right? It sums up the moral of the story, right? I was more thinking the scene where the guy that does the jump to conclusions, Matt, the scene where he's actually being told that he's getting laid off. I think that's the best scene in the movie, because he's first off, this company hires a bunch of hires a team of consultants to tell them which of their engineering staff to lay off. That's the premise of the movie. And this guy's he's getting told by the consultants they're going to lay him off. And he's like, but I talk to the customers so that, no. I'm a people person. I talk to the goddamn customers so the engineers don't have to. Right? So customer needs, we need a people person to talk to the customers. The engineers turn those into functional requirements. So these are the things we need our design to do in order to fulfill the customer needs. Functional requirements are cool, but this means like we need to be able to transport humans at 60 miles an hour. That could be a functional requirement for a car. It doesn't tell us how to make it, right? Once we've got functional requirements from our customer needs, we make design parameters. If we have design parameters, now these design parameters, this is the art in what I call the process from art to part. The part is the thing the customer wants to hold in their hand, right? The art is the design parameters. So this is solid model, drawings, specs, solid model. Solid model is a software thing, so it's the product of a software like SolidWorks or Creo or AutoCAD. It's the model, but yeah, solid's a really bad word there, huh? I don't know. We call it a solid model. It's totally not solid. It's just zeros and ones in computer memory. Solid model, drawings, specifications, the stuff that I suppose it gets down to purchase orders, right? The stuff that we need to communicate between the designers over here to the manufacturers over here. Okay, so we've got customer needs, functional requirements, design parameters. This is the meat. This is engineering here. Going from here to here is design engineering. The designer's job is to somehow get from customer needs to design parameters. The design parameters have to convey enough information so that the manufacturers can make the part by developing process variables that can fulfill the design parameters. All right, so this is the process of going from concept. So when we're thinking about the customer needs, we have a concept. We maybe get a concept in our mind of the thing that'll solve the customer needs. Turn that into functional requirements, design parameters. Then the manufacturing people pick the process variables. Today, we're focusing on process variables, these PVs well, we're going to focus on CNC machining because we focused on CNC machining in this class. I think there'll be cool information if I click the slide button. I don't really, but if I just hit the space bar, it's going to start the countdown video again. Or if I click on the slide, it's going to, I tried this time. I really tried. Oh, this is cool. This is what happens when we screw up the process variables. There's more. There's all kinds of videos about that. So if we screw up the process variables, tools blow up, things break. All right, depart process variables, okay. All right, we looked at this yesterday, right? So the cutting tool coming through, the chip forming. We're going to first start off with the 4 most important process variables in CNC machining. Does anybody off the top of their head know what the 4 most important process variables in CNC machining are? You think they might be feeds and speeds? Let's see what I can do here. Not that one. Work offsets. All right, so let's list some process variables that we can think of in CNC machining. All right, so I heard somebody say feed. I heard somebody say speed. I heard somebody say work offset. What are some other process variables we can think of in CNC machining? You know, I remember having this problem 2 years ago. I don't think they've changed chalk suppliers since then. I solved it by bringing in sidewalk chalk from my kid's stash. And at least the chalk didn't break. I'm not sure it erased very well. So the depth, feed speed, yeah, depth of cut. And so you said draft also. And so that could be like the angle of the part relative to the tool. Was that what you mean? Okay. So in like casting and molding operations, things like that, the draft angle. So the draft angle is like if you ever notice like who's ever used like a red Solo cup? You ever notice how they stack together? Is that a design feature because the customers wanted them to stack together? It may be that the customers appreciate that they stack together, but you can't manufacture them without having that angle on them because you need to be able to get the tooling out. And if it was straight up and down, the friction would be so hard that you could never get the tool back out of it after you made the cup. Stuff like that. So that's a draft angle. But the I think what you meant more was like the orientation of the stock material. Maybe not, but I'm going to say that anyway. We do get to choose that as manufacturing engineers. We get to choose the angle at which we put the stock material in the machine. What's another process variable? Something we say again? The fixturing. What else? There's more. Yeah. So yes and no. The designer chooses what type of material the part will be made out of. We get to choose the shape of the material and how we receive the material. So we do get to choose the stock material, but not actually what material it is made out of, with some gray areas there. So if one of the design parameters, for example, is to achieve a specific hardness, you could buy material that's already that hardness and try to machine it. Or you could buy softer material, machine it when it's softer, and then heat treat it to make it harder after you're done with the machining. So we do get some choice in the material. So I'm going to say stock material. But I'm going to put that asterisk because the material properties the designer chooses. We don't get to choose those. What else? What else? I got feed, speed, work offset, tooling, depth of cut, stock orientation, fixturing. These two things are coupled, right? Fixturing, stock material. What else do we choose? So the person who said tooling, what did you mean when you said tooling?
The material the tool is made out of.
Okay, so you mean like the cutting bit itself, the part of the tool that's going to interact with the workpiece, and the bit that's going to hold that cutting tool is also part of that tooling. But the machine tool we're going to use so you guys have used mini mills, Haas mini mills, and Haas ST10 or SL10, depending on which lathe you happen to be standing at. So the Haas mini mills, I think at the peak performance, the spindle motor delivers about 6 horsepower. But at 6,000 RPM, it's probably delivering like 4 horsepower or something like that. It's about 3,500 RPM. It's delivering 6 horsepower to the cutting edge of the tool. What if your cutting process requires more horsepower? Yeah. You may have to change your process variables to reduce the amount of power required. That's what next week is going to be about, is figuring that stuff out. Or you get a machine tool that has more horsepower. If you go into Washburn 108, not the room we're using for the lab, but the one right next to it, you find a Haas VM2 in there. That spindle has 30 horsepower. That is, what is that, 35 times more than the mini mill. You can make bigger chips. You can make parts faster. You know, we used to use that machine exclusively to make the Y blocks. How long did it take to do the Y block operation where you're spiraling down with the big face mill, making the thing? Anybody remember? I remember. It's 8 minutes. When we ran that operation in the VM2, it was just over 2 minutes. and the chips hitting the glass door that you were standing in front of sounded like machine gun fire. It was a really cool way to do that lab exercise, but we only had one VM2. We couldn't have all of you do it at once. We could have gotten the timing figured out. We could have gotten everybody through in a time period. But when we went to the COVID rules, we wanted to be able to space people further apart from each other. And that's why we get you at the machine tools by yourself now instead of lined up in a line. But 30 horsepower is a lot more than 6. So the machine tool that we're going to use, now this also includes the type of machine. So we said yesterday that we're doing a turning operation. It's really good at making axisymmetrical parts. If we're doing a milling operation, it's really good at making prismatic parts, especially ones we can see from the top, right? Features we can see from the top. You could have a part where you start it in a lathe and you turn some features on it. Then you put it in a milling machine and you make some flat features on it. And then maybe you put it back in a lathe and you make some other features on it. So the type of machining process that you're going to use, we get to choose that. That's a process variable. What else you got? Yeah.
The tool path.
The tool path itself. And the tool path has a lot of options. So the tool path includes the depth of cut. It also includes a width of cut. We often, in speaking of machining processes, group width of cut and depth of cut together, and we call them both depth of cut. One of them is the axial depth of cut. The other one is the radial depth of cut in a milling operation. How far down do you go aligned with the axis of the tool? Axial depth of cut. How far over do you step between passes in our tool path? Radial depth of cut. In Esprit, they call it step over and incremental depth. But the terms axial and radial depth also apply. All right. Tool path. What else you got? Anybody? Time of day. Operators. I mean, I could say name, which operator. I don't care what their name is, but which operator is important. So that's how I'm going to abbreviate it. Time of day, operator name. Ball game. Oh, that's not a variable. We don't get to choose it. Never mind. I do have a good story about Red Sox scores, though, and manufacturing. It's a project with a company that makes golf club shafts. So not the whole golf club, just the shaft. The part that the head goes attached to, the grip goes attached to the other end. What gets a golf club from the rack to the cash register? Why does the customer choose to buy the golf club? Well, that was the premise when they were buying a golf club, yeah. Everybody that's not rich that plays golf just gets their golf clubs for free from their rich friends who bought new ones. Right? So I see some heads going up and down. I've never paid for a golf club. Not true. You guys remember Building 19? It was a discount store that used to be in the Central Mass area. I once bought a driver, no, a 3-wood at Building 19 for $8. It's pretty cool. Golf club shafts. What gets a golf club shaft from the rack to the cash register? One, you have to have some disposable income. You have to decide you want to buy it. 2, you pick it up. Maybe you do this with it a little bit in the store, but you look at it. And if it looks good, you walk over to the cash register and you shell out your $50, $60, $100, $200, whatever it costs, right? It's the way that shaft looks, the way the head mounts to the shaft. All purchase decisions are emotional. Any logic comes into the fact after you've made the purchase decision, and then you're trying to justify it to yourself, to your wife, to your golfing buddies. It doesn't matter who you're justifying it to. Okay, it's how the golf club looks. Gets people to buy it. as a generic, we usually talk about Joe, the guy that works in the factory line. And I was like, yeah, there's Joe over here. And it's just sort of a generic term that I've always used. In fact, this guy's name was Joe. Not just my generic Joe term. Joe was the guy at the end of the manufacturing line who picked up each shaft, looked at it, and decided if it was good. This was their inspection process. It's a valid inspection process because it's eyeballs that get it to the cash register. It's not a horrible process, except failure rates would skyrocket every day after the Red Sox lost because Joe was in a bad mood and nothing looked good enough to Joe when he was in a bad mood. We replaced Joe with a laser scanning system that, regardless of the baseball scores, always gave the same rates. And then Joe got to go do a better job. Automation does not always put people out of work. Joe got to do something more exciting. But who the operator is a huge difference because Jimmy would not see the same flaws that Joe saw, right? Jimmy doesn't know how to use the machine as well as Joe does. So Jimmy's going to make more mistakes perhaps, right? So who the operator is, time of day we do it. Is the sun shining in the window on the machine tool column? That will cause thermal expansion. That will cause things to change. We get to choose these things or put a shade. This is a pretty good list. Would you believe that you could keep writing all day long? There's an infinite number of things that we could impact by changing and making a setting that will affect how well the parts come out. Because really, setting our process variables will determine our ability to meet the design parameters. All right, the 3 most important process variables in CNC machining are listed on the board. Not in that particular order, though. Who thinks they know what 3 they are? Who thinks they know what one of the 3 is? Yes. Fixturing is super important, not one of the 3. Anybody? Yeah. Feed is one of the 3 most important process variables in CNC machining. What else? Speed is one of the 3 most important process variables in CNC machining. We'll explain why in a minute. What's the 3rd one? Is it the stock material? No, because there's different stock material for different parts, so that couldn't be the generic answer, right? All processes have it. All machining processes have it. It's important to all machining processes. Yes? The tool you select will impact the choice of this variable, but it's not the tool by itself. Yeah. The tool path is impacted by the choice of this variable. The work offset is for the convenience of the operator when they're running the machine, or the convenience of the programmer when they're writing the program. That's a horrible way to do it. The programmer should make the work offset be for the convenience of the operator, because that's the one that takes more time and costs more money. It's not the work offset. Yep. The depth of cut. I say 3, but it's really 4, right? Because the depth of cut and the width of cut. The feed, the speed, and the depth of cut, which, by the way, were the main characters in the haiku that started the lecture, huh? I kind of did not bury the lead there, did I? I led with it. Yeah, actually, so that particular haiku was developed on an airplane flying from Boston to St. Petersburg, Florida, where I was bringing a bunch of WPI staff members, and we were going to a meeting that was being hosted in St. Petersburg to talk about machining. And so we actually came up with that one on a committee, as a committee. But But as soon as we realized carbide explosion was the right number of syllables, there was a haiku there. All right, feed speed, depth of cut. Everything, though, that impacts the way the part comes out that we get to change is a process variable. I mean, the building that we chose when we built our manufacturing company was a process variable. It may be something we can't affect anymore once we've started machining, but it was a process variable because we, as the manufacturing engineer, could have impacted it. Feed speed, depth of cut. Why do you think I say that those are the most important process variables in CNC machining? Some people would say it's the stock material or the cutting tool that you choose. Certainly the tooling manufacturer, the cutting tool manufacturer is going to say the tool has a big impact, right? Yeah. Because the feed speed and depth of cut control the physics of the chip formation on the side of the cutting tool, on the cutting edge of the cutting tool. This feed speed and depth of cut control the physics of how we're able to make that chip. Also, the feed and speed working together, well, depth of cut, they control the rate at which we can make chips. The rate at which we can make chips, it has a significant impact on our national economy. The faster we can make, so we agreed, well, I agreed for you yesterday, right? All you have to do is remember that we agreed and answer the quiz question correctly. You don't have to actually agree with me. I hope that I can convince some of you. But CNC machining is one of the most important processes in the world today. It controls our economy, or highly impacts our economy, which then impacts our ability to live the way we want to live, right? I want to live better. The faster we can make stuff with CNC machining, the better we're all going to live. So that's why I say these are the most important. Next week is going to be all about understanding how these impact that. All right, we've introduced process variables, right? Cool. I'll do some videos here. If you want to go through the slides, you can watch these videos. We talked about this yesterday. Turning, the workpiece rotates, right? Milling, the tool rotates. I did my funny joke when I said the tool rotates and I spun around. Waited to see if anybody chuckled. I did it again too, huh? We just did our list of process variables in CNC machining. Okay, we talked about this one yesterday. I'm going to switch from exit solo. And this one. Got it. Okay, so we talked about speed yesterday, didn't we? We started the lecture yesterday talking about speed. The speed of the tip of the helicopter rotor blade is the same as the speed of the cutting edge on the tool. All right. They may not be going the same speed, but it's the same formula. Right? Okay. What's the formula again? So let's look at our cutting tool. I practiced for years to be able to draw circles on the board like that. I had my seventh grade pre-algebra teacher or something. He could do that. I don't think this one was that good, but it was pretty good for the first one in almost 2 years. I've had a lack of circle drawing on the board because of COVID. It's set me back emotionally and, well, like elbow flexibility, I guess. All right, so if this is our cutting tool, say it's got 3 flutes. It's asymmetrical. They actually make asymmetrical end mills like that, where there's a bigger gap between 2 of the flutes or 1 of the flutes or something like that. It actually helps reduce the chatter in the machining process. So when you guys said tool, the tool that you choose is a process variable. The tool material, material that it's made out of is a process variable. The geometry of the tool is a process variable. So the angle of the helix that goes up, the number of flutes, all that stuff, those are all process variables. Mostly here, I'm not a very good artist, though. That's why this one's asymmetrical. It's actually a round also, or unround, or yeah. This is the bottom of the tool. If this is the center of the rotation of the tool, if we spin the tool, it doesn't matter if the tool's round or not, the rotation will have a center. Is that correct? Okay. If this is the center of rotation of the tool, what's the surface speed there? 0. You know why I go over this so many times? That will appear as a quiz question on every quiz from here until the rest of the term is over. I guarantee that some version of this. It'll be in the final exam. And some of you will get it wrong on the final exam. That's why I'm trying to at least don't get that question wrong, because I feel really stupid when you screw that up. That means I couldn't even teach you that where there's no rotation, there's no speed. All right, so 0 there. What is it out here? What is it at the outside of the cutting edge? Pi, oops, that's not a pi. Pi times diameter times RPM. How come that's not what this says? SFM times 4 divided by tool diameter. Oh, it's to go the other way around, right? So we need to reverse this equation because this gives us equals SFM. So pi diameter RPM equals SFM. That's what we derived yesterday. We invented the equation yesterday, right? So let's solve that for SFM. And we're all mathematically convinced that this is true. We may have to adjust to get units right. So right? Yeah. So we want RPM. I need SFM divided by pi times diameter. My daughter's in 8th grade. I think she was in 6th grade is when they started looking at stuff like this, 6th, 7th grade. She'd get really angry when I would do that so fast. It's like, what do you mean? Why? I was like, well, because the things cancel. And it was tough for her. You guys got it though, right? Because you wouldn't be WPI students if you didn't get that. All right. But here it says RPM equals SFM times 4 over tool diameter. Why? Many people have never derived this. They work as machinists and manufacturing engineers, and they use that equation all day long, and the tools do not explode. Why is that equation the same as this equation? Yep. There's some margin of error. There's certainly rounding errors in that one. Yes. Yeah. So 12 divided by pi equals 4. Ish. Yep.
Does this only work for imperial? Does it not work for metric?
Oh, absolutely.
Okay.
You must be using inches.
Yeah, the diameter is 40.
Inches. Those are inches. These are feet. So this is inches. So diameter is always measured in inches for a tool for English units. And RPM is revolutions. Surface feet per minute is so I will leave you with another haiku at this moment. And this one will help you in every class you take from here on out. You ready? Who's ready to write it down? Really? Because you just watched the video. Oh, I'm going to have to start talking faster because I listen to my videos at 2x speed to make sure I know what I said to you guys. And some of the words sound like it's my normal speech, which means I slowed down to half my normal speed when I said that word. I'd learned to talk faster. I also, haiku though. Engineering's math. Just a bunch of word problems. Cancel the units. If the units work, you have probably derived the correct equation. Not necessarily, because I could have used the wrong length here, but still it could have been the tool length instead of the tool diameter. It wouldn't get the right answer, but the units would have canceled, right? But always check to see if the units cancel. When you get the wrong answer on your quiz, it will be because you have the wrong units somewhere in your equation. Almost, or you can't remember if the 12 goes on the top or the bottom, like I can never remember. But if you do the units canceling, you can figure it out. Okay. Speed. Let's go back. This one. Let's go back to this one. The speed that we're talking about there the speed that we're talking, come on, there we go. The speed that we're talking about there is this velocity. I shouldn't write on the thing, huh? Is this velocity here. That's the speed of the cutting edge moving through the workpiece material. So when we look at this picture here, and this picture is going to be dominant next week. This is foreshadowing. That's the word I was looking for earlier. Foreshadowing. We're foreshadowing next week. This is going to be important here. This is the speed at which the cutting edge of the tool moves through the workpiece material. It comes from the rotation of the tool, comes from the rotation of the spindle. In the lathe, it comes from turning the workpiece. In the mill, it comes from turning the tool. Velocity here comes from the rotation of the spindle. What's this? Well, so it's T1, right? It's clearly labeled on the diagram. T1. T1 is the uncut chip thickness. T2 is the chip thickness. Which one of those is a process variable? Yeah. T1 is a process variable. We decide what T1 is. I'm going to show you in a second how to do that. What is T2? So process variable is also an independent variable, right? In science, we call it an independent variable. In engineering, we call it a process variable. T2 is a dependent variable. T2 is going to depend on what material it is, what the speed is, what T1 is, how sharp the tool is, all kinds of things like that. How do we know what T2 is? Yes. No, they will not be equal. You would think. And if this was just like pieces of paper laying down and you went in between two pieces of paper and you bent one of them up as you went along, that would be true. But we're applying thousands of pounds of force in this region on the part, and we're smushing the molecules around when we do that. And we're changing the internal structure of the material right at this region of the cut. And so T2 will not be the same as T1. I suppose it's not impossible that they come out the same, but they're going to be different. T2 is usually thicker. To find out what T2 is, you make the part and you pick up the chip out of the bottom of the lathe or out of the bottom of the mill. So you have to measure T2. You need to find that out experimentally. T1, we got like 3 minutes left, right? Nope, not camera control, close. Room control, up. By the end of the term, I'll know how this stuff works. Let's look at our turned part here. We drew this yesterday, right? Here's my tool. So yesterday I drew the tool with a more angle there. This one, the tool's kind of going that way. It's feeding in this direction, right? Every revolution, it feeds a certain increment. We call that the feed per rev. The feed is distance, is length units. So it'll be length per revolution. That's units we like to use for feed. So it's a speed, but we're using units of length per revolution. How far does it travel for each time it goes around? The chip is forming here and flowing out in that direction as we feed this way and it spins this way. Remember I said in this diagram over here, we're looking straight down this line, and that's the point where the cutting edge happens. So what's the uncut chip thickness? It's how far it moves for each revolution. So the uncut chip thickness here will be this length, the feed per revolution. As long as, let's zoom in on the tool now. So if we have our cutting operation and our tool has an angle here. So before I drew the tool straight down like that, right? In the case where this angle is 0, so the tool's straight up and down, the uncut chip thickness equals the feed. If that angle is 0. If that angle is not 0, then the uncut chip thickness, are you going to draw the triangles and the parallelograms and stuff to figure out what that thickness is, right? The height of the squashed parallelogram times cosine of the angle. And we call that the side edge cutting angle. I often use the Greek capital beta to designate the side edge cutting angle. And so in some of the stuff I've got, you'll see beta there. But it is the side edge cutting angle. It's how tipped the tool is in this orientation as it feeds this direction on the tool. What's the cosine of 0? 1. So my equation works out, right? Feed equals T1 when the angle is 0. When the angle is not 0, it's cosine of the angle times feed to give us our uncut chip thickness. That's a good place to end because that's where we're going to start on Tuesday next week. Oh, wait, you had a question. Wait, before you guys go, I told him to ask me something in class today so that I could tell all of you. I don't remember what it was, though. That's why I told him to remember. Office hours. So we will have throughout the term on Wednesdays and Fridays open office hours in the lab for people to come in and work on CAM. If you're behind in doing lab exercises, we can set that up, but it should be scheduled in advance. Normally that'll be staffed by PLAs. This week, because we don't have our budget finalized for hiring enough PLAs to staff that, it's going to be staffed by me. So if you come in tomorrow, I'll be in the lab all day. It's on you to find me, but I will be there. Find me and I can help you out with CAM, with stuff at the machine tools, or with other questions about the class. By all day, I mean like 10 to 4.